Welcome back. This is PLTW's POE material testing. This is section 2.3.1. All right, this section is going to be talking about destructive and non-destructive testing. So we got to talk about what is destructive testing. Well, destructive testing is not what it sounds like. It isn't blowing something up. What it is it's destroying something to test its physical structures. Can it withstand a certain amount of force? So you take a sample. Here's some examples right here, and then what you do is you can hit them, you can pull them apart, you can compress them, you can shear them, you can do all the various different types of tests to see if the material can do what the manufacturer is saying it can. Non-destructive is exactly what it is. This is actually looking at the material that is actually being used. And of course, you don't want to destroy the material that you're about to use, like let's say your pipes. So what you're going to do is you're going to be using stuff like X-rays or ultrasounds and machines that can look at it without actually hurting the material itself. So first off, let's talk about one of the basic, most common type of destructive testing, and that's called the tensile test. What you do is you take a piece of material, this example of this is a piece of steel, and you get what is called a dog bone. So you put it on a lathe, you turn it until it has this shape. They call it the dog bone because it has two nubs at the end with a narrow in the middle. Here's another example. You can do it with any material, steel, aluminum, or any other kind of material. And then what you do is you pull on it. And with that, you put it on a machine and it's going to give you this graph. The amount of force compared to how much it stretches. Now, there are going to be four regions when you pull on something. The first region is called the elastic region. This is when you pull on something and it snaps back to its original shape. Even metal will exhibit this. You can think of it when it comes to like bobby pins or paper clips. You can bend it ever so far and it'll snap back to its original position. But if you bend it too far, it will then go into what's called the plastic region, where it's going to deform. And it's going to deform up to a certain region. And eventually it's going to reach this point where you reach failure, or that's when it snaps and breaks. And then right here at the very pinnacle of this curve is called the tensile limit, or the load limit. This is the maximum amount of force an object can hold without that particular thing. So, stresses versus strains. Stress is the load, how much force you have over the area. Strain is the amount of stretch over the original length. And then if you can do that, if you take those, you can calculate your stresses over strains. So here's a calculation for stretch or stress. If you apply 430 pounds, calculate what will happen. Well, you take the 430 pounds over the cross-sectional area, which is this is going to be circular. So you take that 0.125 times pi time squared, and that's going to give you this. You calculate that, comes out as 3,500 psi's worth of stress. Then strain. This is your change in your amount over the total length. I want you guys to calculate that. Alright, so you put in the amount that elongated, 0.0625 inches, over the full length. Now, this is the important part, over this length, not the 3 inches. So you want over the length that it's actually stretching, because this part and these parts aren't actually stretching. Alright, so again, to repeat this is your elastic range when it stretches back. Here, there's no permanent deformation. The modulus of elasticity is proportional to this. So you can look at the stress over strain is equal to your modulus of elasticity. This measures how stiff the material is. The bigger it is, the more it's going to resist being bent. Now, once you reach this point, you're going to reach what is called the yield point. Past here, you're going to get deformation. Now, resilience is going to be the amount of area underneath this curve. And this is going to be that's going to be a triangle. So that's how much it can be resist change. Now the offset yield point, that's going to be where you take 2.2%, or sorry, 0.2% of the line, and you're going to put it out a little bit further. This is a tolerance. So you can tolerate up to this much stress and strain, and up to 2.2%, and that's going to give you a nice long linear line. Now you're going to reach plastic deformation. This is where you cannot return to its original shape. It will be forever hardened. And even if you try to bend it back, you cannot rebend it back to its original. It's called work hardening. You can bend a paper clip, but you cannot rebend it back exactly the same way. Then you have that tensile limit right here at the top. That's where you actually have forced it to have its most amount of force. But it's also when it is strongest. You can actually get pre-stressed out material where the stress is actually purposely stressed out and it's actually deformed prior to you using it, and that means it's the strongest it can be. And then eventually, like I said, there was failure where it breaks. Now we can look at ductile, something that's very ductile versus brittle. So this will bend and move while this will snap in half. Now toughness is the area under the whole thing, and that's how much it will take to break, like how much energy it has. So if you have any questions, please ask your teacher.